Hello everyone, my name is Simon Delaval. I'm the Chief Technical Officer for Veolia Nuclear Solutions UK, and today I'm going to talk to you about our remote handling system that we've designed and deployed in Japan for the investigation of fuel debris inside the Fukushima damaged reactor. So first, I'll talk about the mission and objective of this campaign inside the primary containment vessel. Followed by an overview of the remote handling system that we have designed, looking a bit more at the technologies that are inside. And then I'll talk about how we had a design integrated approach to solve a complex problem of this amplitude. And finally, I'll touch on a few other use of technologies to support the operations, training, and installation across the globe. So, investigation of the primary containment vessel at Fukushima. So the investigation of the primary containment vessel in the reactor number 2 of Fukushima Daiichi is a project that we are doing for Mitsubishi Heavy Industry, also known as MHI, as one of the key first steps in the fuel debris retrieval campaign. That's the objective, to remove all the radioactive material at the end of it to leave a reactor clean of the debris. It's a project that is supported by ARID, the Research and Development Group for Japan, and METI, the Ministry of Economy, Trade and Industry for Japan. That environment is by deploying a variety of sensors and scanners, for example, 3D laser scanners, gamma scanners for the radiation mapping, as well as other topological sensors like structured light sensors. And these will allow us to have a fully characterized 3D map of the actual present environment of the damaged reactor with radiation mapping to have an idea of the hotspot, the repartition of the waste, which allows then the strategic planning of the second steps. To make the life a little bit easier, it's a very extreme environment. So as you can imagine, there are very high radiation, especially close to the core of the waste. We have designed to survive dose rates in excess of 1,000 gray per hour, on total dose up to 1 million gray. The environment is unstructured, has moved, damaged after the explosions. So we have to have the ability to navigate around obstacles that we may not be aware of today. And as an additional challenge, the main access to that environment is done through something called the X-export, as you can see on the screen on the right. That is a long, narrow tunnel, effectively, of a little bit more than 550 millimeters diameter, on a total length of 4 meters. So we have to deploy through that tunnel before accessing the inside of the primary containment vessel. And as the containment is critical, the structure integrity of the environment is not known, we've not been allowed to interact heavily with the environment. So the entire system has to be cantilevered and supported from outside the primary containment vessel. So here you can see a 3D animation of the early concept, so quite early on in the project, where we're demonstrating how an articulated boom can be deployed from outside the containment vessel through that X-export tunnel I was talking to you about to access the reactor building environment. And once inside the primary containment vessel, we have to navigate through the obstacles, go underneath the reactor inside the pedestal plinth that is supporting the reactor itself. And once below the reactor, you can see the green control rod at the top here, so you can imagine the reactor being above. So once inside, we're going to perform various levels of scanning, 3D, gamma, to fully characterize this key part of the environment to have an idea for the next step where the radiological hotspot and nature of debris are. So the remote handling system that we've designed is simply called PCVI, Primary Containment Vessel Investigation System, and I'll give you a brief overview of the different technology and solutions that are inside it. So the PCVI system comprises various modules. You can see the main ones on the screen here. The main important one is the airtight cell itself, also referred as enclosure, and it provides an extension of the containment boundary of the PCV. And the airtight cell is connected to the X-export access, as we talked about before, through a knife gate valve. So we've got a double door system between the PCV and our system to allow retrieval and access to the PCV area. Inside it, you've got the main robotic equipment. We call this a boom, as it's a long, slender structure in the horizontal position with multiple articulation. And the aim of the boom, as you see in the video before, is to deploy a few sensors inside the reactor. And on the sensors and the tools required for it are stored in storage inside that airtight cell. On the way we've gone about replacing and reconfiguring the system with different type of tools and sensors is by using our own proprietary force feedback manipulator called Dexter that gives you remote handling, dexterous access to all the tasks that we need to achieve inside that airtight cell. And we also have import and export ports that allows us to have new equipment coming in or export old equipment for replacement. Here you can see a photo of the boom, the PCV boom itself, as it was in UK before we shipped it to Japan. Once deployed, it is of significant length, up to 21-meter reach with the tools and sensors at the end of it, and to be able to be deployed with a constrained environment and navigate around the obstacles and access the area of interest. We got more than 18 axes of motions that are controlled through servo motors and control systems. So the VLS capability touch on all the disciplines, obviously the mechanical and electrical design for this bespoke equipment in high radiation, but also with the capability to deploy control system for complex robotics in a remote environment. We had to design bespoke actuators for that environment due to the high torque required for such a system, but also to the extremely high radiation, as well as a harsh environment, as there is a mixture of water ingress and dust ingress in that environment. And to control these motors, there's a significant amount of cables required. There are no electronics on board, so we had to work with companies and partners to deploy specific materials to have many hundreds of wires through the system through very small bending angle. And as I said before, the entire system is designed for extremely high radiation, up to 1 megagrade total dose. As I said before, the main purpose of the PCVI boom is to deploy a variety of sensors and tools. And I mentioned the sensors for characterization of the environment already. But what we've not touched on yet is to access that area, there are obstacles that have to be removed. So we have a variety of cutting tools, such as hydraulic shears, as well as high pressure water jet cutting, to perform the removal of these obstacles along the way. And they require their own services each. So one of the main roles of Dexter is not only to do the mechanical handling and configuration of these tools onto the boom, but also to replace the services, whether it's water, pneumatics, hydraulics, or electrical services for these tools on the entire length of the boom for each deployment. And this is all possible thanks to our Dexter manipulator system. Dexter is a force feedback remote manipulator that allows us to operate at a long distance from a control room that can be up to 8 kilometers away from the operating environment. And thanks to the combination of force feedback, the cameras on the system, as well as the wide range of motion, the operator can perform tasks that he can normally do with 2 hands and gloves. So such tasks can be removing or placing fasteners, placing cables, handling objects, as well as using a variety of tools to perform multiple tasks that you can normally not do with a robot system. Moreover, the system has been completely designed to be radiation resistant to very high level as required by the projects, and have a contamination prevention system for it, so it's perfectly adapted for the nuclear world. Okay, and now you can see there are many different strands to this project with different systems, different requirements, environments we have to move through. So I'd like to spend a little bit of time to talk to you about the integrated design approach and the various tools that we have used to make a project the success it is. So the first thing is, when we design a system, it's not only about meeting a specification to the letter, but it's about making sure that it's an operational success. So throughout the entire life cycle of the project, we make sure to iterate and validate as much as we can early in the process and along the project life cycle. So we can do that for the most complex tasks with digital tools or physical trials, and make sure that the experience and validation comes back into the design lifecycle. So for example, for this project, and it's quite usually the case in industry, we have a design team working a CAD model system with a project data management behind it that allow the team to be integrated in the configuration management of that complex design. However, for this project, and for a project of similar complexity, we integrated in what we call the retina approach. And that is, in essence, to use and develop the operational tool that will be used later on for the actual operation on site. So you can see on this diagram, not only we have the CAD model as it's traditionally used, we're also developing the user interface, the human-machine interface that will be used to drive the system. That interface includes the control software that's been designed by the team to operate the machine. And on the top, you got the digital twin system that is using the VR4 robot platform from our partner Tracy that allows to visualize in real time where the machine would be. So during the design and as early as the concept stage, we can drive a simulation of the system being designed in the environment with all the details required using the actual interface. And this allows us to have an iterative design across the lifecycle from concept to detail to build. And we capture all this information in our operational management system. The operational management system is in effect the future operational method statements that will be used for the project and proven during that iterative process. Here you got a close-up view of the digital twin system with the PCVI and all the details that was required for the project. So this is not an animation, it's a real-time integration to the HMI on the control system that the team is using to validate the operation and deployment. We have enhancement to it, so not only we use vibrant colors to make sure the environment is clear and understood by the operating team, but you can also see that there are ghost target position that allows the team to validate that the next step that has been sent by the control system is the one that we want. And this gives the benefits of being able to visualize the approach of the system with cameras that don't exist, but also to give a level of familiarity through the development of the system. Furthermore, what we think is quite different from what you may have seen as other digital solutions, we use the exact same tools to operate the hardware. So the process is reversed. You're going to use the information provided by the operational management system, and the operating team will read this with all the enriched data from the screenshot, videos, test outputs on data sheets to drive the system of this planned operation. They use the same user interface, whether it's the graphical user interface on the computer or the physical interface that they've selected to drive the machine itself. And at the same time, the digital twin will be linked in real time to represent and visualize where the machine is expected to be under these commands. And this is quite powerful. So as I said before, it gives you different visions that you don't normally have with the cameras. It gives you the level of familiarity that you have had by doing the previous operational study, but it also allows you to tweak and reassess the operations in real time. So if you wanted to change the trajectory by a certain amount of level, you can disconnect the digital system from the actual machine, plan the operation again in a digital environment before reconnecting the machine and repeating that exact same trajectory. And these are not tools that are meant to stay within the design team. The great benefit is to engage with many stakeholders to make sure that the value is expanded to its optimal capabilities. So of course we do some of the task study, task optimization during the design process and during the actual test validation. There's also great opportunities to get feedback from the site owners by visualizing what the operation is going to be, by making sure that it's in line with the expectation of these operations. It also allows us to train the operator or the operational team in an environment that is going to be exactly the same as the control room environment they're going to work in. So it's not about immersing them into a digital world that won't exist. It's about the operational team getting the best experience in the actual control room with a physical interface on the software that they're going to use to operate the machine. And as I said before, the same operational team will have the real-time enhancement that this entire ecosystem brings to them. But it's not all about digital. It's about being able to test the system in the best condition possible. And sometimes, and often, it means that some physical mock-ups are required. And you can see here on these videos, the system actually being separated in two to be able to test the different operation in the safest way possible. So on the left, you've got the first deployment of the boom through the obstacles on the apertures that we talked about. You've got a sense of scale here with the people walking by it. On the right, you can see the Dexter operations handling some heavy and stiff electrical cable bundle to be installed on the boom, which is represented with a wooden mock-up in that case. Okay, and our final point now on some of the other challenges we have in this project and how we use some of the technologies nowadays to support this incredible adventure. So beyond the technical challenges to realize this project, we had to finish the build and test the system during the height of the pandemic in 2020 and send it to Japan in 2021, where restrictions in Europe and Western Japan were of a further increase, really hindering the travel possible over there. But thanks to the embassies and support of both countries, we were able to send a UK team in Japan for the activities that are to be performed in the factories of our clients. But at some point during the winter, travel was really not possible. So we took advantage of various technological platforms. The first one was to access the control equipment from the UK into Japan to be able to help and assist the MHI team to perform tests with that complex machine. We also took advantage of the HoloLens technology by Microsoft that were allowing the UK team to see through the eyes of the technicians in Japan and communicate with them in real time through video and audio calls. But furthermore, it was to share dynamically documents in a field of view, whether or schematics or 3D models, to explain how to go on about some of the upgrades and testing that we're doing over there. The combination of the support was a great success for us and for MHI. And finally, this is not something that would have been possible by VNS in isolation, and it was thanks to the strength of the supply chain in the UK that we were able to realize this incredible system. So I won't read them all here, but you can see that we had expertise in airtight and nuclear contamination, digital twin software, sensors, water jet cutting, and all this technology being brought together for this amazing system that is now in Japan. So thank you very much for listening to this presentation. I hope you found it as interesting and exciting as the team has done when we realized this incredible system, and I'll be more than happy to answer any of your questions. Thank you.
Thank you, Simon, for joining us today and for a really interesting presentation and sharing the story of the development of this primary containment vessel investigation system, especially during the pandemic. It was really fascinating, so thank you.
You're welcome.
We're getting questions in from the audience, so I'm going to kick off. Please continue to send your questions and we will follow up on them after the event if we don't get time to go through them all. So the first question we've received is relating to the sensors and tools that you mentioned in your presentation. Can you share some more information? Were these supplied and developed by Veolia, or were they?
Yeah. So there's a variety of tools and sensors. So the cutting tools were developed by us, by the VNS team, due to the remote handling knowledge we already had of these. But a lot of the sensors tools have been supplied by a variety of specialists. Some of them in the UK, like Createch, and some of us in Japan, through MHI and Toshiba.
Okay, fantastic. Thank you very much. So another question is it's a bit more broad, but are you looking to build on your work in Japan for use at other sites, and if so, how and where?
So the activity at the moment is really focused on the Unit 2 reactor for MHI, but the core technologies are applicable to the other similar environments. But the know-how we have through it can be applied to multiple sites, as we've done for other projects in Sellafield and Doenrecht. The design is very specific to the unique constraints of that environment, but we know we can translate that technology to other sites.
Fantastic. Thank you very much. And there's another question sort of that follows along the same theme, and it says, you know, at the moment, this tooling is used for investigation of the reactor environment, but you've equipped it with various other tools, including cutting tools and manipulators of various kinds. I mean, what is the potential for it to be used to remove hazardous materials and other potential applications, Simon?
No, that's a very good question. So the design of this system today is focused on that investigation, so that characterization of your environment, on cutting away any obstacles to access the entirety of the area. However, we are currently deploying the next step of the technology, still with MHI, to retrieve some of the early samples on a small quantity of nuclear fuel and waste from the environment. So absolutely, the tools I've seen today, future tools are more than capable to retrieve hazardous material. And we actually use the DEXA system in other projects to work with any type of hazardous material, from nuclear to other hazards.
Okay, fantastic. Thank you. We've got a question relating to the system itself, and it says, you mentioned in your presentation that the control room can be a maximum, I think, of 8 kilometres away from the boom arm. Can you explain the reasoning behind this limit, please?
Yeah, so the main constraint of 8 kilometers is actually attached to our manipulator system. So to get the right performance of the haptic feedback, that force feedback you'll feel when you use the system, the time for the signal to travel is limited by that distance. So it's as fast as the speed of light gives us the right response time. If you remove that high-tech system from the equation, actually the main system, the big boom deployment on any robots, could be driven from much further away.
Okay, amazing. And I just wondered if you can give me a bit of a personal insight, please, into like the project and delivering it for a Japanese client, and maybe just share a bit of insight into how this would compare to a similar project in the UK, for instance.
Yeah, no, that's obviously been a very interesting adventure to work with a Japanese client and Japanese culture, especially in the Fukushima cultural focus that there is in Japan. It's one of the first of big decommissioning projects that Fukushima has, so they rely a lot on international expertise. So it was interesting to see how we can transfer the UK decommissioning experience into the unique challenge of Fukushima. And there's obviously also interesting cultural differences between Japan and UK and Europe in general. On the time difference, also made an interesting rhythm for that type of project over a couple of 2 or 3 years, in terms of how we communicate, how we plan the actions in advance, and plan the meetings with Japan.
Yeah, I'm sure, and it was really interesting. Could you just recap, please, Simon, on the next steps for this project? I just think that would be good, just to, you know.
Yeah, so this project is about to be deployed in the actual environment at Fukushima at the end of this year. So it's currently near the site in a testing hall for final integration. After this project, we're working on the next step with the Japanese client to look at what is called small fuel debris retrieval, which will consist of going in repetition inside the environment to retrieve physical sample of nuclear waste, and little by little removing the waste from that core area in the reactor building. And this will be followed much later in the Japanese program by the large-scale decommissioning of the actual reactor environment.
Okay, fantastic. That's brilliant. We've actually had another question in relating to potential other applications, and it says, could this system be used within flooded vessels, underwater?
Yeah. So good question too. It sounds like the person knows the environment quite well. The other reactors got different conditions, where some of them more or less flooded than the one we work in. The actual end of the boom system is waterproof and submersible, so it's envisageable that end can be deployed underwater. Currently, the main actuation that gets folded like an accordion is waterproof but not submersible. That will be a step above where we're going. That being said, we have other projects in Fukushima, and some of them consist of deploying manipulator arms underwater in other parts of the site.
Oh, that's really interesting. Thank you very much for that. And so we've just got one final question, and then if anything else comes in, we'll follow up separately. But I just wondered if you could give us an insight into the main impacts on the environment, on using this technology.
Yeah, one of the key know-how we have in the company is to know how to adapt such machinery for high radiation environments. So what you've seen on the screen on the deployment of that system with many, many motors do not have any electronics. So we know how to design system to remove all the electronics on the hazardous zones. That's one of the main challenges when you build these machineries, which usually means they have to be bespoke.
Fantastic. Well, thank you very much for joining us. And we've got a short break. But next, you mentioned Dounreay in your presentation, and we've got a presentation about decommissioning at Dounreay from Gordon Tate. So I hope to see you there. And thank you very much.
Excellent. My pleasure. Thank you very much for having me.
Thank you.